Alright, so in this video we are going to be discussing the limit of sine x over x. Now this is a very kind of special limit, and it's generally used to not prove a theorem, but just to show an example of a specific theorem, and we're going to be using that theorem to help us. Okay, so this is our question. Our question is, what is the limit as x approaches 0 of sine x over x? Okay, that's the question that we want to answer. And the reason that this limit is difficult to do if you don't know this theorem is because, the first thing that you would want to do is you would want to try and pull out this sine and apply the limit to just the x's inside of here. But unfortunately, that's not possible because this is sine x and then it's divided by another function. So you can't just pull the sine out, unfortunately. And so the limit needs to be applied to everything. Well, okay, that's fine. Your next option would be to try and factor some of this. But obviously you cannot factor sine x and x. There's no common factor there. So you can't do that either. So you're kind of stuck. And of course, substitution doesn't work either because you're going to get a 0 on the top and on the bottom, and that doesn't work. So what do you do? What is your next step? Well, your next step is to use a theorem, and that theorem is going to be called the squeeze theorem. Okay, and we're going to kind of prove the squeeze theorem as well. Again, it's not necessarily a proof just because we're only going to be proving it using this specific function of sine x over x, not any general function, but just know that the squeeze theorem works for any function. And the way that we're going to kind of use this to help us is, as you see here on the right, we are going to use a unit circle. So that's a circle with a radius of 1, and that's this red right here, okay? And it would go on forever, but we're only going to be using this top quadrant of the graph. And we're also going to need to have a line, and that line, in this case, it's the line y equals x, but it doesn't need to be the line y equals x. It can just be any line that originates at the origin and goes out from there. Okay, and again, it can be any line. And the first thing that I want to do is I just want to label a few things. So one thing that I'll label is I'll label this angle. Okay, so this angle, we're going to call this angle x. Okay, and we're going to try and keep everything in terms of x. So I don't want x's and y's, I want just x's, or at least that's what I'm going to attempt to do. Okay, so we have this angle x, and then there's a few other things that that I want to kind of define here. So the first thing that we're going to do is we're going to create some triangles. Okay, so the first triangle that we're going to create is going to go like this, and this we're going to call basically the small triangle. And as you might suspect, there's going to be a big triangle as well. Okay, so this is our small triangle. Doesn't really look the greatest, but that's fine. So this is going to be the small triangle. Okay, and it's going to have some sort of a height as well, as we might suspect. Okay, there we go. And this is, of course, a right angle. Okay, and it has some height. So we have our small triangle. The other thing that we have here is we have what's called the sector. Now the sector is this small triangle, but instead of this side going to this light blue line, it's going to go to this red line, or to the line of the circle, basically. So that is the sector. The sector includes this small triangle plus this little area right here. Okay? So this is going to be the sector. And then the last thing that we'll have is we're going to have our big triangle. And our big triangle is just going to extend outwards from our line, and it's going to meet up with our unit circle at the coordinate x equals 1, y equals 0. Okay, so our big triangle is, it's bigger than the small triangle and it's bigger than the sector. It's just this additional area added on top of the sector. So that's our big triangle. Okay? And now there's a few other things that I want to sort of define here, and we'll say that that's a right angle as well. A few additional things that I just want to go over here. The first being, sorry, big triangle. The first being is I want to get the coordinates of this point. So this point is where our line meets our unit circle. Okay, so what are the coordinates of this? Well, of course, it's going to have xy coordinates, right? And we don't know necessarily what those coordinates are, but it does have xy coordinates. But like I said, I want everything to be just in terms of x. So is there a way that I can define this coordinate in terms of just x? Well, there is. I can say that it has the coordinates x, comma, something for y. Or I can say that it has the coordinates cosine x, sine x. Now, if you've taken any kind of physics, you'll probably be familiar with this. But if you haven't, you should still be familiar with this, and it should be fairly easy to see how the x and the y relate to the cosine x and the sine x. So this has coordinates of cosine x, sine x, and we're going to use that to kind of help us answer some of these questions here. So that's pretty much everything that we need to define here. We could also define, the height of this triangle here, because we will need that as well. The height of this triangle is fairly easy to get. Again, we could just say the height of this triangle is y, okay? But if we want everything to be in terms of x, we can say that this actually has coordinates tan x. There we go. Tan x. So that's the height of our big triangle. So now that we have that, we can actually start doing some math with these triangles. And the first thing that I want to do is I want to compare areas. Okay, so we're going to go areas here, and we have our small triangle, we have our sector, and we also have our big triangle. So what is the area of the small triangle? Well, the area of a triangle in general is 1/2 base times height. And that is just going to be equal to 1/2. What is the base of the small triangle? Well, the base of this small triangle is going to go from here all the way to here. And since we're dealing with a unit circle, we know that that length is length 1. So the base is going to be 1. And we ask ourselves, what is the height of this small triangle? Well, that height is going to go up to this coordinate. So what is that height? Well, that height is y, or as we discussed, it's sine x. Okay, so sine x. And now we can just simplify this to be sine x over 2. Okay? What about the area of the sector? Well, let's take a look. If you don't know the equation for the area of a sector, it's pretty simple. It's just 1/2, and then it's multiplied by whatever this angle is. In this case, our angle is x. So it's just 1/2 x, which we can just simplify to x divided by 2. Okay? And now finally, we want the area of the big triangle. And the area of the big triangle, similar to the area of the small triangle, is just 1/2 base times height. So 1/2. What is the base? Well, the base is the same as for the small triangle. So we can say that the base is just 1. And what is the height? Well, again, the height is y, or we can say that the height is tan x. Tan x. And then again, we can simplify this one to tan x over 2. So we now have our areas. And what I want to kind of talk about now, or convince you of, is to say that the area of the small triangle, the sector, and the big triangle are somehow important to us. And let's figure out how that's so. Well, I would argue that the small triangle is always going to be smaller than the sector. The area of the small triangle is always going to be smaller than the sector. And I would say that the area of the sector is always going to be smaller than the area of the big triangle, right? No matter what this angle is, no matter where this line moves, if it goes like this or if it goes like this, doesn't matter. I would say that uh, the area of the small triangle is always going to be the smallest. The area of the sector is always going to be bigger than the area of the small triangle, but smaller than the area of the big triangle. The only exception to this would be if this angle goes all the way down this way to 0 and we have no angle. In that case, all three of the areas would be the same. Okay, and if you can kind of see that and believe it here, then what you can say, well, you can make an inequality. You can say that the area of the small triangle is always going to be less than or equal to the area of the sector, which is always going to be less than or equal to the area of the big triangle. Okay? And if you do that, you can replace this English with math, and you'll get that sine of x divided by 2 is less than or equal to x over 2, which is less than or equal to tan x over 2. Okay? And if we follow this logic, we're going to now work with this this inequality to try and get an answer for the limit as x goes to 0 of sine x over x. So let's kind of see where that brings us. So the first thing I'm going to do with this inequality is I'm just going to multiply it by 2. Okay, I'm going to multiply everything by 2. That's going to get rid of my denominator here, and I'm going to be left with sine x is less than or equal to x, which is less than or equal to 10x. And now what I'm going to do is I'm going to take this whole thing and I'm actually going to divide it by sine of x. Okay? So now I'm going to get sine x over sine x, well that's just going to equal 1, is less than or equal to x over sine x, which is less than or equal to tan x over sine x. Okay? And now you might be able to see kind of where this is going. So what you should see here is we have x over sine x, which is almost what we want. We want the opposite of this. We want sine x over x. So what are we going to do now? Well, we're just going to take the reciprocal. Okay? When we take the reciprocal, we're going to get 1. And then you have to remember that the signs on your inequalities are going to switch. So now it's going to be that 1 is greater than or equal to, okay? So 1 is greater than or equal to sine x over x, which is greater than or equal to sine x over tan x. And finally, what you should be able to realize is that tan x is just a function of sine and cosine, and so you can simplify this on the right hand side as well. You can just say that 1 is less than or equal to sine x over x, which is less greater than or equal to just cosine x. Okay, so now that we have this, we can finally talk about the squeeze theorem. And what the squeeze theorem is telling us is going to help us solve the answer for the limit as x goes to 0 of sine x over x. So here is the squeeze theorem. And again, this wasn't necessarily a proof of the squeeze theorem. This was more so just a trying to introduce the squeeze theorem and then use it to solve this particular question. But the squeeze theorem does apply to any function that you give it, so long as it meets the appropriate requirements. What are those requirements? Well, let's say if we have some functions, if we have the functions, let's say g of x, h of x, and f of x, so we have 3 functions, and g of x is less than or equal to f of x, which is less than or equal to h of x, okay, within a certain limit, within a certain range, let's say. Okay, so g of x isn't always going to be less than or equal to f of x, and h of x isn't always going to be greater than f of x. But within a, little area of our graph, we want it to be that way for certain. Then what we can say is that if we find then the limit as x goes to some number of the function g of x equals some number L, and the limit as x goes to some number a of the function h of x equals L. So if the limits for g of x and h of x are the same number, then the limit as x goes to a of f of x also equals L. That's what our squeeze theorem is telling us. Okay, so it's telling us if we have some function, in this case, some function g of x, in this case that function is just 1, and we have some function h of x, that function is cosine x, right? So g of x and h of x. Then our middle function, f of x, in this case sine x over x, is going to have the same limit as the functions of g of x and h of x, given that those limits are the same. If those limits are two completely different numbers, well then the squeeze theorem doesn't help us. Okay, so finally we can go, okay, let's solve this question. So let's solve it. Let's take the limit of our left function and our right function and see if they are the same. And if they are, then the limit of our middle function is also the same limit. Okay, so let's find the limit as x goes to 0, not of sine x over x, but of 1. Okay, so what is the limit as x goes to 0 of 1? Well, that's just equal to 1. And we ask ourselves, okay, what is the limit as x goes to 0 of cosine x? Well, if you remember your cosine graph and what it looks like, that's also equal to 1. Cosine at 0 is 1. Okay, so since the limit of the left-hand function and the limit of the right-hand function both go to 1, then we can say with certainty, due to the squeeze theorem, that therefore the limit as x goes to 0 of our function sine x over x is equal to 1. And we can say due to the squeeze theorem if we want. Okay? So the squeeze theorem here helped us determine that if we sandwich sine x over x in between the function y equals 1 and y equals cosine x, we found those limits of y equals 1 and y equals cosine x, and therefore we were able to find the limit of the sine function. And again, this works for this specific function, but it also works for other functions so long as this inequality holds true and so long as the limits here are the same, and in this case they are. Okay, and I want to kind of show you why this is the case, and so that's why I have this picture here to help us kind of take a look at what we're dealing with. Okay, so what I want to kind of talk about here is this bottom function, this green function, is the cosine function. Okay, so this is cosine of x, and this top function is y equals 1. Okay, and y equals cosine of x, and then this green function is the function y equals sine x over x. Okay, and what you can see here is that within this short range in between -2 and +2, and a little bit further on, the function sine x over x is indeed basically being squeezed in between two other functions, those functions being y equals 1 and y equals cosine x. Okay, and basically what we're saying is that since the limit of y equals cosine x it exists and we can find it, and the limit of y equals 1 exists and we can find it, and since these two functions are basically sandwiching our function sine x over x in between them, then whatever the limits of those two functions are, so long as they're the same limit, again, that's important, so long as they're the same limit, then the function that's in the middle that's being squeezed by them also will have the same limit. So we can kind of indirectly find the limit of our middle function by making sure and ensuring that it's squeezed in between two other functions, and we write that mathematically with our inequality, right? We wrote 1 is less than or equal to, or maybe greater than or equal to, it doesn't really matter, sine x over x, which is less than or equal to cosine x, okay? So we mathematically write this using these signs, the less than or equal to or the greater than or equal to signs. And we sandwich it in between those two functions, y equals 1 and y equals cosine x. We find those limits, and then we're able to get the limit for sine x over x. Okay, so I know this was a long video, but that's kind of an introduction to the squeeze theorem. Again, this wasn't necessarily a proof, but just know the squeeze theorem does work for any function so long as they fit in this inequality and so long as the outer limits of the two outer functions are the same. Okay, so that's everything for this video, and I'll see you guys in the next one.